Hello, welcome, and a very good evening. Today we are continuing our quest to learn x86 assembly language, the language that is basically driving all the PCs even today, although we will stick to like the very old parts regarding the 8086 and 8088 processors. Maybe we'll sprinkle in some 286 opcodes in the future, but none of the modern extensions, the 64-bit ones, etc., because we are staying very retro here. And I'm using Oscar Toledo's book Programming Boot Sector Games as the reference basically, and all my examples are taken from there. So if you want to follow along at home, you can get this book from his webpage nanochess.org as an ebook, hardcover or paperback. And yeah, I think it's a very good book. It is using a lot of nice example programs that are getting rapidly more and more complex. So we'll see how we can deal with that. But yeah, it's very instructional and easy to read for such a relatively advanced topic, I would say. And today we want to have a look at the DIV instruction for integer division, as well as how to actually debug an assembly program using MS-DOS based tools. There are probably also other ways to do that, but again, we want to stay retro here, and I'm going to use an old debugger that is easy enough to install and use. Very short introduction to the div opcode. What we're gonna do here is we want to print out a number, and we're doing this by recursively dividing the number by 10 so that we can get all the digits in the number. For example, if you have the number 123, we need to get the digits 1, 2, and 3 and print them out one by one. And the div operation will help us with that. The div operation always takes whatever is in the AX or DX-AX register pair, if you have 16-bit or 32 bits in your integer number, divides that by whatever register or memory address you give, and the result will be either in the AL 8-bit register or the AX 16-bit register, and the remainder will be in AH or DX. There's of course also the 32 and 64-bit enhanced versions of the div opcode, but as we're not talking about 32 and 64-bit operations here, we will leave that out because we are staying like in the 80s. Good. So I already created an empty file called number.asm, which is basically similar to all the other programs that we had. And if you haven't watched any of my previous videos, you should go back and start probably at part 1. Library 1 ASM will stay the same, but I also created a library 2 ASM for new stuff. And what we're going to do is we will put some value into the AX register, and let's say we will put the number 12,345 in there. Then we will want to call a function that is called display number, and then a new line. I think I called this just new line. Yeah, that's what I called it. And the question is, how do we do that? So let's make a label here, and at some point down here we'll also return from the function. We basically need to iterate over all the numbers that we have here, 1, 2, 3, 4, 5, and collect all the digits from here. And the easiest way to do that is to divide by 10, which will give us 1, 2, 3, 4, and as a remainder we will get 5. Then we get 3 and the remainder 4. 12 and 3, 1 and 2, and in the end we will get 0 and 1. And then we can print out all the digits. Once we reach 0, we can print out all the digits in the reverse order, 1, 2, 3, 4, 5, and get an output on the screen. We can use the stack for that. Once we did the division and have the remainder, we can push the result onto the stack. And once we are done with all the divisions, we can recursively again pop the elements from the stack and print them out. Okay, this is the theory. How can we do that in real life? Well, first of all, we will do a 16, we only have a 16-bit value, but we will, actually we could in theory do a 16-bit division, but to be on the safe side, we are doing a 32-bit division. So I'm gonna load up the dx with a 0 here. Dx ax will contain the value. Caller only gives ax. So we only get 16-bit input, but we want to have a real 16-bit division. Then we will load up the divisor, that is 10 into cx, and we can call div cx, which will give result in. What does it say here? In ax, result will be in ax, remainder in dx, which is nice. And now, as I said, cx will contain 1, 2, 3, 4, and ax will contain the 5. So we will push the 5 onto the stack, push remainder on stack to collect later. So there we are pushing onto the stack because then we can pop in the reverse order and print out in the reverse order to have correct number here. Then we have to see, is the ax 0, because then we reach the end of our loop. If result is 0, we are done dividing. So if that is the case, jump if equal. The equal flag will be, the equal flag or 0 flag will be set when we do the compare ax 0 is actually 0. And then we go to another sublabel called display number 1, which we'll put down here. And if that isn't the case, we still need to divide further. So we call our function recursively, print out all numbers, and here divide recursively. And the beauty of this is the call display will put the current address plus 1, namely this new label here on the stack, which means once we return, we'll automatically continue taking numbers from the stack and printing them out. And the taking from the stack is just simple pop ax, take number from stack. Then we convert to ASCII by adding the 0, because otherwise we will get a weird ASCII character, and if we add the 0 character, we'll get the correct letter on the screen. So this is basically a convert to ASCII. And then we call display letter, which is a function that we already had, and this will print out whatever we need. So quickly, we forgot something here. Yes, we have a small error here. So we are calling display number, of course, and that should assemble. Yeah, that looks nice. Now we go to DOSBox and execute number.com. We get 1, 2, 3, 4, 5, exactly as we wanted. However, if you want to see how this actually works, we can execute debugger, and in this case I already had Borland C installed, but you can, if you look around, you can find this program here, the so-called Turbo Debugger, or a similar tool on the web. I took it from Borland C. You probably can also get it from Turbo C or as a standalone product or in the Turbo Assembler package or something like that. This is just the one that I had at hand. Other debuggers from Microsoft or from other companies will work very similarly. The nice thing about the Turbo Debugger is that you can use the mouse to, you have Windows basically in text mode. You have a nice overview of the CPU. Here you can see the code that is being executed. Here you see the state of all the registers, like AX, BX, CX, DX, and so on. You can see all the flags, like the 0 flag for comparisons. You can see the contents of the stack, which is also very nice, and also the data segment. And you can do a lot more. Right now, we actually just want to open our file, which is a COM file, not an exe file, and we will take number.com. We get a warning that there's no symbol table. That means we won't have any source files to view, but we don't need it because we're looking at assembly language anyway. And there you already see our program, which is very simple and very short. Here we are loading AX with our 1, 2, 3, 4, 5 value, which incidentally is displayed in hexadecimal, obviously. But to make this easier to see, we can actually go to data and go to inspect. And then we can, for example, write AX as a variable to inspect. And it will be recognized that this is a register of word length, and currently it contains a 0. We can also inspect other registers. For example, I'm also interested in the DX. And we get another window that I put over here. And that's already pretty neat. Now to run, I press F7 to just run the very first instruction and not continue running. It will also trace into any calls that we make, so that I enter into this call here, which I definitely want to do. But here on the right side, you can see that AX now contains 1, 2, 3, 4, 5, or 3039 hexadecimal. So that was already a good thing. That works. Then we jump into our display number function, and you can now compare with the stuff that we have in the Emacs or in your code editor, and you should see the mof dx, 0 and the mof cx, 10 and the div cx. And yeah, that's exactly what we see here. Of course, it's again hexadecimal, so cx will contain a, which is the same as 10 in decimal, div cx, and so on. So let's see what this program does. First of all, we're loading dx with 0, we are loading cx with a. We don't inspect that because that's always the same. Then we divide, and over here we see now AX contains 1, 2, 3, 4, and the remainder 5 is in dx. Okay, so we push dx onto the stack, and voila, you can see here, suddenly the 5 is on the stack. So this is the bottom of the stack, and this is the top of the stack down here. There's the return address from our call, which is fine. We compare AX with 0, which is not equal to 0, so we won't jump, but instead we will call ourselves recursively. So we jump back from here to address 145, which is the start of the function up here. So basically looping. What happens now during the call, it will store the return address, which is 156 hexadecimal. That is the line after the call, which is the pop AX value. Once we have divided all the numbers, it will continue and start taking numbers from the stack. So let's quickly go through there. Mof dx, mof cx, then the division. We get the 1, 2, 3 and the 4. We push the 4 onto the stack. We compare and call again. Next iteration, we get the 12 and the 3. We push the 3 onto the stack. We compare and call again. And I'm gonna skip right through this because it's getting a little bit boring. Now comes the interesting part. Now we have done the last division. We get 0. and as the remainder the 1. So we push the 1 onto the stack, this is the last digit. We compare AX with 0, and this time the 0 flag has been set because the comparison was successful. And now we already see jump if equal is the same as jump if 0 flag is set. And it already shows with an arrow, yes, we will do the jump down there to 156. And executing will show us, yes, we're not calling recursively again, but we continue with the pop AX. So we call pop AX, take 1 from the stack here. Now the stack content 1 is inside of the register AX. We add the 30 to get the character 1 actually, and we call the print function. I'm not gonna do that right now. We can have a look at the screen. Currently it's empty. Then I'm gonna skip over this with F8. So if you look here, step over is F8. We do this once. And looking at the screen, we get the 1 at the left side of the screen. Okay, then it does the return. Takes one return address from the stack and continues with the number 2, calling the print. We get 1, 2, and we can do this all the time until the stack is empty and we are back in our main program. We call the new line function because right now the cursor is still right behind the number. We call the new line, cursor moves down. We call int20 to quit the program. And that's already basically the way you can inspect and debug assembly programs in MS-DOS or in DOSBox using very old tools. And I think this is pretty neat. And these tools are actually pretty powerful, and more modern versions will be even more powerful. But I think this one here, this version from Borland C, I don't know, version 2 or something, is pretty powerful, but also not too complex, so that you can get a good start into this whole debugging business, I'm gonna say. Yeah, but anyway, that's already what I wanted to show you today. I did not want to put too much different things in here. So we learned a bit about the division opcode and how to debug the whole program and how to call functions recursively. I think this display number function is a really elegant solution that Oscar thought up here. You probably can do it in a different way as well, without doing the call operations, but doing rather more, not really a recursion, but doing a for loop more or less, without using the for, but with a lot of jumps and comparisons. But I think this one here is very compact and it does everything that you need, and it's really, really short and relatively easy to understand, I think. So if you like this, please leave a comment, share, like, and subscribe as usual. You can, as always, also support me via Patreon or Ko-Fi. And if you don't want to do that, that's fine with me as well. Just make sure to pop in next time in Let's Code. And yeah, I hope you have a very nice evening.